welcome everybody. So far we had looked at some very basic issues in real time operating systems, and we had seen that task scheduling is one of the major issues with real time operating system, because the application deadlines are met with the help of a suitable task scheduler. So, now we will start looking at some of the schedulers that are being used. We will start with the simplest scheduler. It goes by the name Cyclic Executives. The Cyclic Executives are the simplest real time operating systems. These are run on very simple embedded applications, where there is a severe constraint on the processor capabilities, maybe a 4-bit or 8-bit processor, and the memory is very less. So, in this situation a full fledged operating system is difficult to use. The tasks are simple here and periodic in nature, and these real time cyclic executives are basically very small programs. Let us look at the basic structure of a cyclic executive. So, here initially, to start with, the system is started with a system initialization, where various parameters are set, and then there is a periodic timer which gives timer interrupt, and it is the cyclic executive which starts a call to a program, or executes a program where initially there is a data input, application processing, and then data output, and then it keeps on waiting until the next period comes. So, this is the simplest real time operating system. It is basically a small program, maybe just a few dozens of lines, and here as you can see that just to take an example of how it works is the data input. Let us say that we have a temperature controller. In the temperature controller, initially let us say the temperature has to be read from the sensor. So, that is the data input, and then we need to check that is it below a threshold, higher than a threshold, is it abnormal, etcetera. And then based on that we possibly want to show the current temperature reading on a display. So, that is the data output, and then we wait for the next interrupt, and the cyclic executive continues looping here infinitely, each time waiting for the interrupt, doing some simple processing. So, this is the simplest real time operating system run on the most elementary embedded systems. One thing to note here in that in these cyclic executives there are no processes. It basically involves running program. A program initially samples some sensors, then does some processing, and then calls some display. And here this program is executed a number of times, and each time there is an interrupt, this program is run. So, now let us look at more examples of operating systems which are sophisticated compared to the simple cyclic executive. So, all these schedulers that we are looking at are at the simplest end of the real time operating systems, and these are called the clock driven schedulers. The ones that are much more sophisticated are the event driven schedulers. So, we had in the last discussion seen that there are two broad categories of real time task schedulers. One is the clock driven schedulers, the other one is the event driven schedulers. So, now we are just mentioning that the simplest end of the real time operating systems, we have the clock driven schedulers starting with simple cyclic executives. Now, let us look at slightly more sophisticated clock driven schedulers. So, all these clock driven schedulers, the clock interrupt comes at regular intervals. On the rising edge of the clock interrupts come, and as soon as the clock interrupt comes, the scheduler becomes active. So, these points at which the clock interrupts come, these are called as the scheduling points. And in our last discussion, we had mentioned that the instants at which the scheduler becomes active and checks what to do next are called as scheduling points. And here the scheduling points are defined by a clock. So, some of the important clock driven schedulers are the basic time driven schedulers, or which is called a basic table driven scheduler, which is also called as a timer driven scheduler, and the other is a cyclic scheduler. And even to think of it, a simple round robin scheduling, where based on clock interrupt, the different tasks are run in a round robin fashion, is also an example of a clock driven scheduler, but we are not going to discuss about that. That is used in traditional operating systems. But as far as the real time operating systems are concerned, we are now looking at the simple end of the operating systems, the simplest operating systems used in small embedded applications, looked at the cyclic executive. Now, let us look at more sophisticated clock driven scheduler. First, we will look at the table driven scheduler, and then we will look at the cyclic scheduler. These clock driven schedulers are also called as offline schedulers or static schedulers, because the task set to be handled is known beforehand. It cannot handle sporadic, aperiodic tasks. Only the periodic tasks which are known beforehand, whose period is known, these are handled, execution time and periods. Of course, these might start at different phases. We had seen the concept of phase of a task. So, these tasks may start with different phases, but then that is handled by the clock driven scheduler, the different phases, but periodic and aperiodic tasks are difficult to handle, and even the aperiodic tasks can be handled which do not have deadline. When after completing the real time task, the lax time that is available can be used for handling aperiodic tasks, but sporadic tasks cannot be handled by the clock driven schedulers. So, first let us look at the table driven scheduler, and then we will look at the cyclic scheduler. These are used extensively in embedded applications. So, as we mentioned that these are used in low cost embedded applications having very less processing power and very small memory, which cannot host full blown, full fledged operating systems. So, the advantage of these are these take very small code space, very little storage, the code size is small, and even the temporary storage requirement is very small. And these are very small programs run for a few microseconds, just few lines of code, and incur very less runtime overhead. When the processing power is small, if we want to run a sophisticated operating system, then the overhead of the operating system will be so much that there will be hardly any time left for running the real time tasks. But then even these have the advantage of running efficiently and with less space on a embedded application, but then these have their shortcomings which we must be aware of. The important shortcomings of these are that these are difficult to accommodate aperiodic and sporadic tasks. And now, let us look at the table driven scheduler. In the basic table driven scheduler, we have the operating system stores a table in the memory. This table basically contains only two parameters in the simplest form, that what are the tasks and what are the time for which it will run. The tasks may not be real tasks actually, even though we are calling tasks, it may be just invoking or running certain programs, because handling tasks require sophistication on the part of operating system. The task table, creating task, task state and so on, as we know from our knowledge from a basic operating system. Task handling requires a lot of sophistication on the part of a operating system, and we are now discussing the simplest real time operating system. And here, even though we use the term tasks, but then these may be just running a program. These may not be task in the true sense of a task in an operating system. So, here in the basic table driven scheduler, we have the different tasks and their maximum run time, and then we have a periodic interrupt from a timer, and as the timer interrupt comes, the timer handler routine is invoked. The timer handler routine keeps track of which is the task that is running now, and that is given by the entry. So, it just looks into the schedule table and finds out the which task to run, and just finds out the task, some parameters of the task which tell how to execute, name of the program and so on, name of the executable which is to be executed. And then the entry is augmented to point to the next entry in the table, and it is mod of the schedule table size, because it just keeps on executing that. So, the next time is given by the table entry time dot get time, the current time plus the time that is required by the task. So, here the timer is set for the next time, and that is the time that the task takes. So, from the current time the task is started executing. So, this is the one to start execution of the current task, and the timer is set for the maximum duration of the task. And then as the timer expires, the timer handler is invoked, and the next task is taken out from the table, and the pointer to the table is incremented, the entry, that is the next task to be taken, is incremented, and then the time is set for the timer, and the task is taken up for execution and so on. So, here as you can see, in a basic table driven scheduler, we have a simple data structure that is stored in the memory, and the code is small, and it just keeps on executing this schedule. So, this is also not a sophisticated operating system used for simple applications, but slightly more sophisticated than the simplest cyclic executives. So, here is an example of a schedule table. These are the tasks or the programs to run, and the maximum execution time is mentioned in milliseconds and the timer is set, and just observe here that the tasks are typically the time is in milliseconds. So, the scheduler overhead must be much smaller than the task execution time. If the task execution time is 90 milliseconds and the scheduler itself takes 100 millisecond, then it is not a good idea. So, here the cyclic schedulers are very efficient, run in just a millisecond or so, and then they just set the timer, access the table, and then they start the execution. But one thing that we must notice here is that in a table driven scheduler, we need to set the timer a large number of times, and setting a timer is actually rather expensive task compared to a time it takes for running a task, and also the scheduler overhead. A major component of that is setting the timer. The other things like incrementing the entry count pointer, etc., these do not take much time. Large amount of time is taken in setting the timer. So, this overhead is significant, and the next scheduler that we are going to look at is a bit more sophisticated than a simple table driven scheduler. But one important advantage of the cyclic scheduler is that we do not have to set a timer again and again. Timer is set only once, and the overhead due to setting timer is largely overcome in a cyclic scheduler. Let us look at the cyclic scheduler. The cyclic schedulers are very popular, used in embedded applications. These are also meant for simple applications where there is not enough memory and processing power to run a full blown event driven real time operating system. For example, a microkernel real time operating system, which we will see later, they take several, even a microkernel operating system may take several kilobytes of memory and requires running several thousands of lines of code each time a scheduling point occurs. But here the cyclic scheduler is very simple. It requires running only few lines of code each time a new task is to be taken up for scheduling. So, let us look at the cyclic scheduler. So, here again let me just mention that even though we are saying tasks, but these may not be real tasks, because these are used in simple real time operating system. Here we do not have capability to manage tasks. These are actually simple programs that are stored, and the scheduler just starts executing these programs. These are not tasks in the actual sense of the task as used in the operating system literature, but that for uniformity of treatment across different schedulers, we are using the term task, but we must remember these are not tasks in the real sense. So, here if we have n periodic tasks and each task requires running at different period. So, it is that in the simple cyclic executive there was only one period, but here there are multiple periods. So, which are we called as multi-rate operating system. In multi-rate we have multiple tasks which require running at different periods. Some may be requiring every 100 millisecond, some may be 500 millisecond, some may be 2000 millisecond, etc. So, the schedule here is stored in a table, as in the case of other cyclic scheduler, that the table driven scheduler, which is repeated forever, but we will see that it overcomes setting a timer again and again. So, we have n periodic tasks. Then let me ask this question, that to repeat the schedule, what should be the period of repetition? Let me rephrase, that if we want to develop a schedule for these n periodic tasks, each task requiring running at different time intervals, some may be 100, some may be 250, some may be 300 millisecond, etc. So, what is the maximum length for which we need to create the schedule and store it in a table, and then we keep on repeating it forever? So, the answer to that is LCM. So, we take all the periods and then compute the least common multiple. So, if we have 100, 300 and let us say 400, then we need to store the period, the schedule for a period of 1200 millisecond. So, 100, 200 and 100, 300 and 400, the LCM is 1200, and therefore, we need to maintain the schedule for 1200 millisecond and then keep on repeating that. So, this 1200 millisecond, or the maximum period for which we need to maintain the schedule, is called as a major cycle. So, after every major cycle, we repeat the schedule, but in the major cycle is divided into many minor cycles. The minor cycles are also called as frames. So, as you can see these lines here, so these are basically clock interrupts, and these define the frames. This is a periodic timer. So, it needs to be set only once and then keeps on giving interrupts at this interval, defining the frames. And to each frame a task is assigned, and that is stored in a table, and these points at which the frames start, the frame boundaries, these are the scheduling points. The cyclic scheduler becomes active at these scheduling points and then decides which task to run, and then the table is stored for one major cycle, and then the task execution is repeated. So, the scheduling points define the frames, the beginning of the frames, and these are set by a periodic timer which keeps on giving interrupts at regular intervals. And each time there is a interrupt from the periodic timer, the cyclic scheduler is activated, it starts running and then consults the schedule table, finds the next task to run, and then after it completes, it may idle for some time until the next interrupt from the periodic timer comes. So, one important thing to notice is that compared to a table driven scheduler, where the timer was set again and again, requiring much overhead, here that is overcome. The periodic timer is start only once during the initialization of the running of the system. Now, the important thing that we must understand is that how is the frame time set for a given task set, and how are tasks assigned to frames. So, the task instances or jobs are assigned to specific frames, and these tasks have different periods. So, maybe that in one major cycle or a hyper period, major cycle is also called as a hyper period, maybe in one hyper period some task instances, that is jobs, run multiple times, some jobs run only once, etc. So, as far as the cyclic schedulers are concerned, one important question to answer is that how to fix the frame duration and how to assign tasks to the frames. But as we take examples and explain the methodology, we will find that it may be possible that with a given set of tasks and task periods, we may not be able to find a frame size and assign tasks to frames. So, then we need to divide some tasks into smaller jobs or job slices and then retry the methodology. So, compared to the simple cyclic executive and the table driven scheduler, here for the system programmer who is trying to run a set of real time tasks on a cyclic scheduler, the development of the schedule is non-trivial. We will examine what is involved in setting up a schedule, in fixing the frame time, what are the factors to be considered, and given a task set, how does one go about doing it. We will do a number of examples, and we will also request you to try out few examples on your own, so that you understand the nitty-gritty of developing a schedule in a simple cyclic scheduler. So, that we will continue with the next lecture. Now, we will stop. Thank you.